Okay. After learning everything we've learned over the past few lessons, this brings us to optimization problems, which are applications of maximums and minimums. So, certain terms we might see in an application problem would be something like greatest profit, least cost, optimal size, greatest distance. These all refer to maximums and minimums. And if they refer to maximum minimums, then the derivative should be involved. I think in terms of a business standpoint, greatest profit, least cost would be pretty common questions you would come across. So here's probably one of the most basic optimization problems you would come across in a first semester calculus class. It says that a manufacturer wants to design a box, and it's an open box, which means it doesn't have a top. Why does it not have a top? Who knows? Okay, I can tell you that we're doing this one without a top because computationally this works very nicely for an intro problem. If you put a top on the box, it really doesn't change how the problem's going to go. So this question just an open box. So it's got a square base, so the sides of the base are the exact same distance. So this measurement and this measurement are the same. So if we call that x by x, and it has a surface area of 108 square inches. So you have a square base. You want to use 108 square inches of cardboard to build this box. So this side, this side, this side, etc. So if you take all the sides plus the bottom, the amount of cardboard you want to use is 108 square inches. You want to figure out what dimensions you should make the box so that it has its maximum volume so that you can fit the most inside of it. This would be important from a business standpoint in that um, someone doesn't want to use all their money on the packaging of a product. So they decided that they are willing to spend a certain amount of money to have 108 square inches of cardboard for their box. They don't want to spend any more money. They don't want to use any more than 108 square inches because they've allotted a certain amount for the box itself. But they still want to fit as much of the product inside the box as possible. So they want the volume of the box to have a maximum volume. So how can we maximize the volume but be constrained to only using 108 square inches of cardboard? Well, here are a few examples of different boxes and their shapes and dimensions that all use 108 square inches of cardboard. They all have open tops, so it's four sides and a bottom. They all have different volumes. If you did the surface area here, if this was a 3 by 3 by 8 1/4 box, it would have a volume of 7 1/4. This one is a 4 by 4 by 5 3/4 box, is a volume of 92. And you see, they all have different volumes. If you look at the surface areas of them, if we actually computed the surface areas, every one of these would have the same surface area. They'd all use 108 square inches of cardboard, but they clearly all have different volumes. So which box should be used to maximize the volume? So this is your typical optimization problem. So what we're going to do is we're going to have to identify a primary equation and a secondary equation, and there are reasons for this. The primary equation is the equation that you're trying to optimize, what you're trying to find a maximum of. Well, we're trying to find a maximum volume. So the volume of this box will clearly be our primary equation. If the box has got a square base, we can call each one of the sides x, so x by x, and then there's going to be some height, which we'll call h. So if we look at the volume of this box, it should be the area of the base, which would be x by x, so x squared, times the height, so x squared h. That's the equation we're trying to optimize. That's the equation that we're trying to find the maximum for, but it's got a lot of variables in it. When we take the derivative with multiple variables, we could possibly get into implicit differentiation. But remember, to find a maximum, we have to find critical numbers. So then we have to figure out where the derivative is 0, where the derivative does not exist. If we have multiple variables in this equation, while yes, we could take the derivative of an equation that has multiple variables in it using implicit differentiation, it is going to be more difficult to find the critical numbers when we have more variables. So our goal here is to say, well, if this is what we're trying to optimize, can we reduce the number of variables in this equation so that it's easier to find the critical numbers and therefore easier to find the maximum or minimum depending on what we're looking for. Well, that's where the 108 square inches comes into play. That's our secondary equation. Our secondary equation is going to relate the variables in the first equation so that we can reduce the number of variables in this primary. Well, we know that the surface area is 108 square inches. How would you compute the surface area of this box? Well, you take the area of the base, which would be x squared, plus the area of each one of the sides, which is x by x, and there's 4 of them. So there's going to be 4 of these x by h's, and that's our surface area, which has to be 108 square inches. So this equation right here relates x and h to one another, and we can use it to help minimize the number of variables in the primary. So this is our secondary equation. If you look at that secondary equation, I could rewrite it as h equals 108 minus x squared over 4x, just solving for h. I could then take that h and I can plug it in here, and I can get that the volume equals x squared times 108 minus x squared over 4x. If you notice now, my volume equation only has a single variable over here on the right hand side. So then we could take the derivative with a single variable, and then we could find the critical numbers far easier than if we left it as multiple variables. So again, in solving something like this, whenever you do an optimization problem, we're really looking for a primary and a secondary equation. There could be multiple secondary equations. We'll stick to simpler ones right now where we only have a single one. But the whole idea of these other equations, secondary equations, is to reduce the number of variables in the primary equation that you're trying to optimize. So the next steps would be to then look at this thing and say, here's a function. Can I find the maximum on this function? And then that'll help me find the dimensions that maximize the volume. I want the volume to be the biggest. So which x can I plug into here that would give me a maximum volume? So we're going to find the derivative, we're going to find the critical numbers, we're going to test those critical numbers, and we'll go from there. So what we had is we had this equation that the volume was equal to x squared times 108 minus x squared over 4x. That came from the fact that we solved for the surface area in terms of h, and that was that h was equal to 108 minus x squared over 4x. And we use this secondary to help us with our primary. Now, we want to take the derivative of v so we can find a maximum. I'm going to rewrite v so that it's easier to do that. Well, this x squared and this x, we can cancel one of those. I can take this 4 and pull it out. So I have 1/4, I have x times 108 minus x squared. I'll then multiply this x in here. So I have 1/4 times 108 x minus x to the third. All that was simply so that it's easier for me to then find v prime. So v prime would be 1/4 times 108 minus 3x squared. And then what I want to do is I want to find the critical numbers from the derivative. That's where my maximum or minimums could be. Now that would be when the derivative is either 0 or does not exist. Since this is a polynomial, we don't worry about does not exist. But 108 minus 3x squared definitely could be equal to 0. And so that'll occur if we subtract the 108 and divide by -3, it will be when x squared equals -108 over -3, which would give us, I believe, 36. So x could be plus or minus square root of 36. So x is plus or minus 6. So now notice this. X could be plus or minus 6. But what was x representative of? It was representative of the box's base dimension. Well, is it possible for that base dimension to be -6? No. In the function, any function x could be negative, but in this function representative of the base of a box, x could not be negative. So really, if you think about this, we only have this one critical number, x equals 6. and we want to test this critical number. We want to test whether or not this critical number is a maximum, yields a maximum, I should say. Well, it's the only critical number we found, so if it doesn't yield a maximum, then we're really not going to be able to answer this question. So there's a good chance that this is going to work out, but we still want to check it. And we can figure out if 6 is a maximum by either using the first derivative test or the second derivative test. I like to use the second derivative test. In that, I'd have to find the second derivative. Well, if this is v prime, the second derivative would be 1/4 times derivative of 108 would be 0, and the derivative of this is going to be minus 6. And if I plug 6 into there, this is going to be negative. If it's negative, I'm on a concave down picture because I'm second derivative. Concave down picture would yield a maximum value, and so 6 is a maximum. Now if you go back to the question and said, what are the dimensions? Well, the dimensions are x by h. Well, x is 6. So I believe it was in inches. So 6 inches by 6 inches we got to figure out what the height was. Well, remember, we had this equation here that told us what the height was in terms of x. So if you plug x in there, plug 6 in there, you got 108 minus 36 over 24. It comes out to be that h is 3 inches. So the box that's 6 inches by 6 inches by 3 inches will have the maximum volume. It's going to still only use 108 square inches of cardboard to build this box out, but it will hold the most material. And so that's your typical optimization problem. So when we're solving a typical optimization problem with maximums and minimums, what you want to do is you often want to read the word problem and identify what the question is giving you and what they're asking. Okay? So look at what's given and what's to be determined. If you can, sketch. So make a little sketch, if it's a geometric problem like the last one, you draw a little box, label the dimensions, look at what you know, what you need. Then what you want to start to do is identify your primary equation. So that's the thing that is going to be maximized or minimized. That's what you're trying to optimize. Find a maximum volume, least profit. Profit would be the primary. You want to find the greatest distance, least distance, etc. Distance would be the primary. The problem with that primary equation typically is that it has multiple variables in it. So then what we want to do is we want to reduce the primary equations to having only a single independent variable. This is done by using a secondary equation. So what you want to do is you want to take some information out of the problem that relates the variables in the primary equation together and use that to reduce the variables. So once we have that, then what we're going to do is we're going to take the derivative, we're going to start finding the critical numbers, but we're only going to look at the critical numbers that are in the feasible domain of the primary equation. In the last one, we threw out -6. It wasn't a feasible value. So we really only look at the feasible values from the domain of the primary equation, not the entire domain, the feasible domain. Once we have that, then we're going to determine whether we have a max or min using our calculus techniques, either first or second derivative test. Now, remember, the critical numbers come from the first derivative, but we test them either using the first or second derivative and go from there. So here's another typical optimization problem. Campbell's Soup wants to make a can that holds 12 ounces of soup. Find the dimensions that will minimize the cost of the metal to manufacture the can. So there's some problems with the wording of this. There's a conversion of ounces to linear distance. So if I said instead of 12 ounces of soup, let's change that to 12 cubic inches of soup, which isn't equivalent to 12 ounces, but it's going to make more sense. If we have to convert from ounces to linear measurement, that can be kind of tricky. I don't want to get into that for this problem. So I'm going to just change the wording from 12 ounces to 12 cubic inches. Again, 12 ounces and 12 cubic inches are not the same thing, but I'm changing it to cubic inches. All right. Anyway, now what we want to do is figure out what dimensions will minimize the cost of the metal to manufacture the can. So what dimensions can we make this can so that we use the least amount of metal? We know that the volume is 12, okay? That's the amount of soup we want to fit in to this can, okay? But what dimension should we make the can so that the amount of metal we use is at its minimum? So then the idea here is the surface area, which would be the amount of metal, would be the primary equation. That's what we're trying to minimize. So how do you find the surface area of a cylinder? Well, it's a simple geometric formula. You have this area, you have this area, then you have the wraparound rectangle that goes around the middle of the can. And so what you end up with is 2 pi r squared plus the area here, which would be 2 pi r h. So that's just the general formula for the surface area of a cylinder. What we know is that the volume of the cylinder, which can be found using pi r squared h, is equal to 12. So this is what we're trying to optimize. This is the other information given. This is our primary. This is our secondary. So what we're going to do is we're going to take this and we're going to solve this for h. So we get 12 over pi r squared. We're going to take that, we're going to plug it into here. So our surface area equation becomes 2 pi r squared plus 2 pi r times 12 over pi r squared. Notice now we have a single variable r in our surface area equation that we're trying to minimize. I want to take the derivative now. But before I do that, I'm going to cancel. This pi and this pi will cancel. This r and one of these r's will cancel. I'll rewrite this as the surface area equals 2 pi r squared plus 24, that's the 2 times the 12, and this r will come up, r to the negative 1. Now it's very easy for me to take the derivative. This will be 4 pi r minus 24 r to the negative 2. Being r to the negative 2, what we're going to do is we're going to rewrite this as 4 pi r minus 24 over r squared. I can bring this together as a single fraction, in which I'm going to get 4 pi r cubed minus 24 all over r squared. And all I did there was multiply this by r squared over r squared so that the denominators were the same. So this is our derivative. When is that derivative going to equal 0? When is that derivative going to not exist? Well, when the numerator and denominator are each 0. So 4 pi r cubed minus 24 has to equal 0, and r squared has to equal 0. Well, if you solve this, what you're going to find is that r equals 0, but that doesn't make any sense because r is the radius of the can, and the can have a radius of 0, so we're going to just throw that out. We don't need that. While it could result in a critical number here, and it could result in a max or a min, for the problem itself, it doesn't make any sense. Now, as far as this goes, what we're going to do is we're going to say that r would have to be the cube root of 6 over pi. Again, that's just moving the 24 divided by 4 pi and then taking the cube root. So we got one critical number here. If that's the minimum, that's the r dimension we need to minimize the cost. If it's not the minimum, we don't really have an answer because it's the only critical value that's feasible that we could find. So we look at this cube root of 6 over pi. We could take the first derivative and we could figure out what's happening on either side. Is it plus minus? Is it minus plus? Is it increasing, decreasing, whatever, and determine if we have a minimum. But we could also plug it into the second derivative and see what happens there. Notice if I take the second derivative, remember this was the first derivative, the second derivative will be 4 pi. This will become plus 24 r to the negative 3, again pulling this power out. Plugging this into here, you're going to see you're going to get a positive. Second derivative positive, concave up tells you it's a minimum. So r equals the cube root of 6 over pi would be one of the dimensions that would minimize the can. The other dimension that would minimize the can would be h. Well, we need r and h to find out what our dimensions of the can will be. How could we find h? Remember, h was found through this, so we have 12 over pi times the cube root of 6 over pi squared. That's our h. I could further compute what this would actually equal, but that's not necessary. These are the dimensions of the can that would minimize the amount of metal you need to use. If you notice, this problem is no different than the box question, other than in the box question we're trying to maximize the volume. We were given the surface area. Here we were given the volume and we're trying to minimize the surface area. But it's a geometric figure and we're talking about maximums of and minimums based off of volume and surface area. Okay, and here we have a profit equation, in which case we're going to try and maximize our profit. So we have Matteo, and Matteo owns a small company that makes t-shirts. He can produce the shirts at a cost of $2 a piece. The shirts have been selling for $5 a piece. Okay. So we have $2 a piece, they sell for $5 a piece, and at that price he's selling about 4,000 shirts per month. It's pretty good. So then Matteo plans to raise his prices. Okay, raise his prices so he can make a little bit more money. But he doesn't want to raise them too much because then he's going to start selling less shirts. So he thinks that if he raises his prices $1, every time he raises his prices by $1, he's going to sell 400 fewer shirts. So he wants to figure out what's the sweet spot where he can raise his price by $1, each increment of $1, but still maximize his profit. At some point he's going to raise his price too much and he's going to sell so few shirts that it's not going to be worth it to him to produce those shirts. So if we're looking at a basic profit equation, it should be based off of the number of shirts sold and how much he makes per shirt, right? So if you make, I don't know, say 100 shirts were sold and you made $3 per shirt was your profit per shirt, you would have 300 bucks extra on top of the cost it was to make the shirt. All right. So you should understand generally how profit works. So we got to figure out how to come up with a profit equation so that we can maximize the profit. So this profit equation is going to end up being our primary equation. So we got to look at a couple things, right? How are we going to come up with this primary equation? Well, we know that the number of shirts sold is really based off of, he's got 4,000 on average per month, but it's going to start decreasing by 400 for every dollar he increases. Okay, so he's got to figure out every time he increases by $1, he wants to figure out what the number of shirts would be sold. So first thing we're looking at is how to come up with the number of shirts sold. So the number of shirts sold, let's go N of SS. Okay, number of shirts sold. Well, we start off with 4,000 and we're going to subtract off of that. Well, how are we going to subtract off of that? Well, there's going to be 400 per increment of increase over $5. Well, if you look at the difference between the selling price before to the selling price now, it would be whatever the now selling price is minus 5, because the original selling price was $5 a piece. So if I say the new selling price is X minus 5, okay, which would be the increment of increase. So if it was $6, it would be 6 minus 5 and everything went up by $1. If it was $7, 7 minus 5, the increment then went up by $2. And every jump of $1, we know that 400 fewer shirts would be sold. So if this is 1 times 400, then that's, if the difference between here and here is 2, then 2 times 400 would be the amount we would have to take off the 4,000, etc. So the number of shirts sold, this equation will generally give us that value. We can look at this a little bit simpler. We could say, all right, well, let me factor out 400 out of this. that would leave me with 10 minus x minus 5, which I could then write as 400 times 10 minus x minus 5 would be 15 minus x. So simply we can say that the number of shirts sold is based off of this. So that's going to go here. Then we got to look at what the profit per shirt is. Well, the profit per shirt is based off of the cost. Well, the cost is $2. Every dollar above $2 that you sell a shirt for would be your profit. So if you sell a shirt for $3 and it costs you $2, then you have a dollar profit. If you sell a shirt for $7 and it costs you $2, you have $5 profit. So the profit per shirt is really based off of how much you sell it for minus the cost. Well, if we sell it for, say, X dollars minus the $2 of cost, then we can use that as our profit per shirt formula. So our profit equation is going to be 400. Let me rewrite this better. Our profit equation is going to be 400 times 15 minus x times x minus 2. Now, if you notice, we didn't have a secondary equation. But in some ways we did. We just worked through the secondary equation into the problem by using this x minus 5 and this x minus 2. I mean, I could have used different variables to start and then essentially taking some of these pieces and plugged them in to reduce the variables. But, you know, the way we work through this problem, I think, just using some common sense, we kind of avoided that secondary equation. All right, so then this is our profit equation. We're going to have to take the derivative of this profit equation. One way to take the derivative of this profit equation could be to use the product rule. Or what we could also do is multiply this out before we take the derivative. I'll leave the 400 out here, but I'll have 15x minus 30 minus x squared plus 2x. If I then take the derivative, the 400 is a constant multiple. 15x's derivative is 15, 30 is 0, x squared is minus 2x, and 2x would be 2. So if this is my derivative, which I can rewrite very simply as 17 minus 2x, I need to find the critical numbers for this. Well, 17 minus 2x equals 0 will be one critical number. That'll happen when x equals 17 over 2. Remember, x is a amount of money, okay, that he has to sell the shirt for. Remember, sell the shirt for $5, $2 minus the cost of the shirt, profit per shirt would be 5. So x represents the selling price. Okay, even when we looked at x over here, represented the selling price. And so x of 17 over 2 is our only critical number. If that results in a maximum, then there's our value that we want. Okay, typically when we talk about this as a number value as money, we wouldn't write 17 over 2. 17 over 2 is the same thing as 8.5. This is all in terms of dollars. So basically $8.50 is what we're looking at here. So hopefully this results in our maximum. Well, we can either do that by looking at the first or second derivative. I'm again going to go to the second derivative. In looking at the second derivative of this function, it would simply be 400 times negative 2. And so the idea is if I take this and plug it into the second derivative, there are no x's in there, so this is always negative. If it's always negative, I'm always going to be concave down, which by default would make this a maximum. So the selling price of $8.50 is basically my sweet spot. Okay, $8.50 would be my sweet spot in terms of that's the amount of money I should sell a shirt for. If I sell the shirt for more money than that, I'll sell so few shirts that my profit starts to decrease and my profit will go down. Even though maybe I'm still making money, my profit will go down. So the idea of profit is you want your profit to increase to the point where you make the maximum amount possible. So we look at this and we say, okay, well, looking at this profit function, looking at how much we would make if we did $5 a shirt versus how much we make if we did, say, $8.50 a shirt, both cases will make money, but the one that would give us the maximum profit would be the $8.50. You can then figure out how much would the profit be by simply plugging the $8.50 into your original profit equation, and you can get the exact amount of money you would make as a profit. Okay, so we have one more. This is a more geometric problem. It says, okay, we have a rectangular page. That page contains 24 square inches of print. So we look at the print in here. This area is 24 square inches. Let's say this is y by x is the dimensions of the print. Okay. The margins at the top and the bottom, though, are specified to be 1 inch on either side and 1.5 inches on the top and bottom. So then if you look at the dimensions of the page here and here, if this is y from here to here, and this is 1 inch and this is 1 inch, then this will be y plus 2 inches, and this will be x plus 3 inches. Okay? So we have two things. We have the dimensions of the page and the dimensions of the print. We want to use, if you look, what dimension should the page be to use the least amount of paper? So ultimately what we're trying to do is we're trying to minimize the dimensions of the page to minimize the paper. So dimensions of the page would be y plus 2 by x plus 3. But the print is 24 square inches, and that's found by doing x times y. So back to this is just a primary equation, this is a secondary equation. We can take this and say, well, 24 over y equals x. We can take that and plug it in there, and we get our page dimensions to be y plus 2 times 24 over y plus 3. Now that's what we're trying to optimize, so we're going to take the derivative of that equation. We have it down to one variable, very simple to take the derivative. So we're going to use the product rule or distribute this out first. I'm going to distribute out first. It's going to be easier. 24y over y times y would be 24, then 3y, then minus 48 over y, which I'll write as y to the negative 1, and then 6. So we take the derivative. 24 is 0, 6 is 0, 3y would be 3, and this will give me negative 48 y to the negative 2. So I have 3 minus 48 over y squared, which I can also write as 3y squared minus 48 all over y squared. So when does the derivative equal 0? Well, when 3y squared minus 48 equals 0. When would the derivative not exist? Well, that'll be when y squared equals 0. But y squared equals 0 will be when y equals 0. Feasibility, that can't work. You can't have this dimension be 0. So that's out. This one, 3y squared minus 48 equals 0. That's going to be the same as y squared equals 16. So y is going to be plus or minus 4. Negative 4 is out because you can't have your dimension be negative 4. So basically just have y equals 4. So looking at y equals 4, if that results in what we want, which is a minimum, then we're good. That's our answer. We can do that using the first or second derivative test. I'll go use the first derivative test since we've been doing the second derivative test for a lot of these. We got 4. We're looking at the first derivative. I'll plug in 3 and 5 into this derivative. Okay? So plugging it, sorry, that's not the derivative. This is the derivative. Okay? Plugging it into the derivative, you see that when I plug 3 in, I'm going to get 27 minus 48, which would be negative. Plug 5 in, I'm going to get 75 minus 48, which would be positive. So if we're decreasing and increasing, there's your minimum. So y equals 4 will result in a minimum, but that doesn't answer the question. What dimensions should the page be? Well, the y value should be 4. If x times y is 24, since y is 4, that tells me x has to be 6. Again, that still doesn't give me the dimensions of the page, because the page is y plus 2 by x plus 3. So then the dimensions of the page would be y plus 2, so that'll be 6 inches, by x plus 3, which would be 9 inches. So the dimensions of the page would be 6 inches by 9 inches, and that would use the least amount of paper. The area of the page would be at its least and still contain 24 square inches of print.